Okay, good evening, everyone. My name is Mike Mogadam. Welcome to the July meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. If everyone could please be seated so we could start the meeting. There's a lot of faces I haven't seen in a long time, so it's welcome and it's nice to see you. A special welcome to some people that were at the Cube Gallery's Nocturne event last night. I noticed a few people that said they were going to show up and have indeed, so that's nice. We got a nice program and a full program tonight. Regular features, of course, are Al Scott and Gary Boyle. We have something that has been of interest to me for quite a few months, and I think we're in for a real treat. Frank Marshall is going to talk about the very peculiar shaped cloud pattern on the North Pole of Saturn. Okay, Frank's done a bit of research on that, and he'll share with you his findings. Stéphane Pape is going to give an update. We all know him as the fellow that's spearheading the astronomy park. He's going to give an update on the work he's done lately. He's done a lot of work lately, so he'll give a quick update on that. Break is when we hand out our tickets, or I should say, collect the. I'm forgetting the word. The tokens for the door prizes, and we'll actually hold the door prize after the break, after the meeting. After our 10-minute break, Richard Alexandrovich is going to talk about exoplanets and what's next for Kepler, given that it's in its let's say the last lap. You know, there's still another lap to go, but he'll talk about what's next. And finally, another subject that's been of much interest to me, Glenn Ledrew, our resident optics expert, is going to talk about optical aberrations in telescopes. So I'm looking very much forward to that. Okay, then follow with observations. A little humor to start the evening here about the cow that jumped over the moon and forgot about re-entry. Okay, so lots of new members. Two new members, Andrew and Stéphane. Welcome. I know, Stéphane, you're here. You'll be talking a little bit later on. Andrew, are you here? If you are, say yes. Okay, so maybe you're quiet. You'd be surprised the number of people who I say, are you here? And the new members, and then somebody will come up to me in the break or after the meeting, and they were in fact here. We just took stock of all the members since the beginning of the year. This is really good. I hope we continue to offer value to you, and I hope you'll enjoy it and learn from the experience. One thing that Chris reminded me to say is that Art Fraser, and part of the Art and Ann Fraser, who take care of the beverages and snacks, just outside the door there to the auditorium. Art will hand out the membership cards. Okay, so you can pick up your membership cards if you're a new member from him.
Or renewal.
Or renewals, thanks. Okay, members in the news. Karen Finstad. Karen, are you here tonight? It's been a while since I've worked with you on outreach. Thanks, Chris. Karen has been appointed the new National Secretary for the RASC, so that's really good. She's part of the Ottawa Centre here, and awesome news. So congratulations, Karen. Okay, well, the Lagoon Nebula, what's new in the news here? Well, this is the July issue of our calendar, and of course it's an image from Deborah and Peter Sarvolo, and this is the Lagoon Nebula, of course. Only they could do something quite as beautiful as this. So some fine work from them. Wanted to say a few things about the Nocturne event, Nocturne 6, I believe it is, at the Cube Gallery last night. So, as you know, it was a real toss-up with the clouds. Depending on which weather forecast you looked at, one would say clear skies from 9 o'clock till midnight, and the other one said it ran the full spectrum of forecasts from clouds to rain. Well, we had maybe about 2 minutes of an opening for where we saw Saturn, and we zoomed in on it as quickly as we could. So it was I think what strikes me about this evening, what makes it very memorable, is the fine conversation. I really enjoyed speaking to fellow members and to people who are clearly passionate about this and who are very interested in this. People who come back year after year. So hopefully clear skies again next year. There is a follow-up event next Thursday, July the 10th. Not as big as this one here in terms of the lights being turned off on Gillian Avenue. That won't happen, but nonetheless, it's another opportunity for in working with the Cube Gallery and really making ourselves popularizing what we do.
But how many people were at the Cube last night?
Not many. I would say about 75. I didn't go inside the Cube Gallery. I'm sure there was, I'm sure there was a lot of people inside, but outside, man, tops 50, 75. So, okay. So, oops. Oh, thanks, Chris. All right, let's move right on to Gary Boyle and Ottawa Skies this month. Thanks.
Good evening, everyone, and welcome to Ottawa Skies for July 2014. First slide, please. That's actually first slide. Second slide, please. So here we have Hercules, and Hercules is my monthly article because I do write the monthly article for the national website, and a lot of the graphics I'm showing tonight are also in the article too. So Hercules does have, it's actually the kneeling man, which is actually upside down. You'd think so. The legs are up here, and his club is down here, and here's the keystone. Well, other than M92 up here, M13 is a wonderful globular cluster. It's huge. Hercules is the 5th largest constellation in the entire sky, just over 1,200 square degrees. And other than the two globular clusters, there are a lot of galaxies. So next slide, please. So here we have M13, globular cluster. I like to put perspective whenever showing things and looking in the sky too, because when astronomy first began, people thought everything was just one-dimensional pretty well, just like the holes in the ceiling in these tiles. But it's not. As you can see, the star over here, Hipparchus 81848, is only 1,800 light years. But now M13, wonderful globular cluster, but 1 million stars, they believe, is in this cluster. It's just a huge supercluster. 25,000. So behind the flag, over here, NGC 6207 is about an 11.1 magnitude galaxy and 62 million light years. But the real piece of resistance, if you can see it with your telescope, is 15.3 magnitude. It's IC 4617, 500 million light years away. And I've seen this. It's just amazing what the human eye can see. So when people say, how far can you see with this telescope? Well, 500 million light years, not too bad. Next slide, please. Well, this month, usually I don't speak too much about asteroids, because there's really nothing much to look at, but the one main thing is on the night of July 4th and July 5th, 2 asteroids, Ceres and Vesta, which are the 1st and 4th in size, are actually coming very close together in the nighttime sky. And just for relation, here's Spica, and here's Mars coming down to meet Spica on the 13th. So the two will be very close together. In fact, Ceres is magnitude 8.4, and it'll be 347 million kilometers from Earth, and Vesta is about 264 million kilometers. So although they look as if they're going to collide in the sky, they're very, very far apart. So that'll be something to see on that one night, or 2 nights, that is. And next slide, please. Yeah, and these are the two. In fact, this is with the Dawn spacecraft. They got a real close-up view of Vesta. It's 570 kilometers wide, whereas Ceres, taking with the HST, is about 1,000 kilometers, and that's actually number 1. So it's the largest asteroid. Okay, next slide. Does anybody know what a damocloid is? Nobody knows what damocloid is. Okay, a damocloid is actually the dead nucleus of a Halley-type comet that has outgassed. It means it has no more stuff. It doesn't have a coma, it doesn't have a tail. But this guy, next slide please, did come to life. It's comet C 2013 UQ4 Catalina, and it's actually come to life. And you can see that from July 8th to 13th, in fact around July 10th, it'll be closer to the Earth. It's going to move through the sky pretty good. It was first observed in May when it was only 13th magnitude, very, very faint, and all of a sudden, as it rounded the sun, it just brightened up. So these things usually don't brighten up, but there must have been some outgassing or some splitting of the nucleus, and just hopefully created enough to stay lit. So if things do stay very well, and hope that they do, we'll see the comet, which is fourth magnitude, or no, not fourth, sorry, seventh magnitude, around the 10th. And again, if you get on my article on the website, it'll show this too. Next slide, please. So here was the little guy when it was first detected, and perihelion is on the 6th, but close to the Earth is on the 10th. Be about 7th, just a little fainter than what naked eye visibility. And it's really going to boot through the sky, 7 degrees per day, or the full moon at about 102 minutes. So that's really going to move across the sky. But the fastest comet I've seen is, who remembers comet Iris-Araki-Alcock back in '83? That thing, that was 30 degrees per day. And literally, you'd see it in a telescope, and you would see it move against the background stars extremely fast. So hopefully this guy will move. It'll be bright enough, and maybe some RASC photographers can actually image it for next month. Next slide, please. And of course, the digital moment will be on the 5th. Spica and Mars, along with the pretty well first quarter moon, a little less than first quarter. And like I said, Mars moving back over here, so on the 13th, will be just north of Spica, 13th of the month, and of course keep moving eastward. Okay, next slide. Yeah, and just the time again, perspective, how close things are. Mars is, well, the moon, light seconds, Mars light minutes, and Spica, 263 light years. Okay, next slide. And this is my only gallery shot. I decided to show it now that I've taken from South Mountain. I can speak about, objects in the sky till cows come home, but just to see this, stepping on the balcony at 2 o'clock in the morning is just nirvana for me, but we do have nirvana that we go to. But just to step out and see this is truly amazing. It never ceases to amaze anyone who's been under the canopy of stars along the Milky Way. Words can never describe what you're actually seeing. Next slide, please. And here's your famous favorite lunar phases. The full moon on the 12th will be the buck moon. The next day, on the 13th, the moon will be even closer to Earth, about 356,000 kilometers, which is pretty well the closest, which means very, very high tides. So those are in boats, so watch it. Or also, if you're in the pool or in the bathtub, be safe, okay? Don't want anyone drowning because of high tides in your pool or bathtub, please. And that should be about it. Nope. And again, this is if you get on the Ottawa Centre website, ottawa.rasc.ca, and just do e-news, and it'll get to my article, which has a lot of these graphics tonight. So until next month, we'll see you in 4 weeks. Thanks, folks.
Thank you, Gary. Something we haven't heard in a couple of months now, and I welcome back, is Al Scott with his 10-minute astronomy news update. What's current in astronomy news? Thanks, Al.
Thanks, Mike. So it's good to be back. I've spent a little bit of time over the last month at a couple different astronomy meetings. One was the Canadian Astronomical Meeting in Quebec City. The other was a photonics astronomy hardware meeting in Montreal. So I thought it would be interesting. A lot of the stuff that Canada is doing in astronomy is probably not well known to everybody. And what facilities Canada is involved in, where does Canada spend its budget on astronomy? So I thought my first item would be, what's Canada's current standing in professional astronomy facilities? So the Canadian Astronomical Society puts together a long-range plan every decade for what they believe is the things that Canada should be spending money on and what facilities they should support. This slide shows some of these interesting things. The highest Canadian priority for the decade starting in 2010 is participation, a major participation partnership role in the 30-meter telescope right here. This is one of the planned extremely large telescopes. The European one is also in motion. This one is being led by the Michael and Betty Moore Foundation, as well as the California universities, and the Canadian Association of Canadian Universities has been involved in it. It's a segmented telescope. There's about 750 1.2 meter segments in here. And Canada has asked for $300 million to become a partner. The time, however, the clock is running on this, and the government needs to make a commitment by the end of this year, or Canada's possibly going to be kicked out. We've already spent several $1 million, and the actual Canadian contribution to this would be the dome itself, which has been designed by Dynamic Structures in British Columbia, which is a roller coaster manufacturer, if you believe that. The TNT Consortium, all the other partners have their funding in line, but Canada's been given a 1-year extension to join the crew, as it were. Other Canadian contributions, Canada has, up until recently, been a partner in the James Clerk Maxwell telescope on Mauna Kea, which is a millimeter wave telescope observatory. But Canada is pulling its operating funding from this, along with the Netherlands and the UK, in favor of contributing funds to the ALMA, which is the Atacama Large Millimeter Array here, which is the new telescope, which I've shown you some results from over the past couple of years. A really cool array of radio telescopes. But all is not lost for the JCMT, which is a really good facility. The East Asian Core Observatory Association has stepped in to take over operating the telescope. And this is a kind of a new group of strange bedfellows, the Japanese, the Chinese, the Koreans, all getting together to do astronomy. Interestingly, Canada is also a contributing partner to the 8-meter twin Gemini North and South telescopes, one of them on Mauna Kea, one of them in Chile. The UK has pulled its funding from this observatory, but again, the East Asians have plans to step in and pull up some of the slack. It looks to be possible that the East Asians are actually taking over Mauna Kea, moving in funding into some of these failing scopes to have a site similar to the European Southern Observatory site in down south in the southern hemisphere. So that's a good thing. The Canada-France-Hawaii telescope is also on the summit of Mauna Kea operating. It's been operating for a long time, about 25 years now, I believe, and it occupies some of the best seeing conditions in the world. But it's only a 4-meter scope, and it's getting old. It's in need of an upgrade. So Canada is putting together a plan to upgrade it to a 10-meter telescope, segmented Keck-style spectroscopic telescope, and they're looking for international partners to contribute to that. Canada is also a small partner in the Square Kilometre Array, phase 1 of which is being built in South Africa and Australia. Here's an artist's conception of what it's going to look like. Again, a radio telescope. Canada's contribution to this is about 12 million euros. In space astronomy, Canadian astronomers are involved in several high-atmosphere balloon-borne missions looking at cosmic background radiation. You're probably familiar with the MOST telescope, the micro-oscillation of stars, miniature space telescope. Here's a picture of it here in scale next to the James Webb Space Telescope, which is planned to go up in 2018. Canada has cut the funding for for the MOST telescope and planned to turn it off in September. It's exceeded its operational lifetime by quite a ways. We're also building a small contribution to Japan's Astro H X-ray telescope. It's like a $5 million laser metrology system that we'll be adding to it. Overall, Canada's annual budget for space astronomy is decreasing now that we've delivered our contribution to the James Webb Space Telescope, the Fine Guidance Sensor. So Canada's budget in space astronomy is going down from its highs of 10 to 15 million a year. They plan to drop it down to about 4 million a year after this. In comparison, NASA's is about 700 million a year, and Europe's is about 500 million euros a year. So it gives you an idea. In per capita terms, Canada's space budget's about 1/5 of the US's per capita. So that's 1/50th in actual terms. CSA, however, are considering a potential 1-meter class space telescope called Castor, which could potentially go up in 6 years, roughly speaking, if it gets funding. The Canadian Astronomical Society has asked for $100 million for either a contribution to this Canadian-led space telescope in the ultraviolet, or else participation in the US's WFIRST mission, which is a dark energy exploration mission, a major wide field infrared observatory. So just gives you kind of a flavor for what Canada is doing. Canadian astronomers are really well respected in the field, despite the low budgets that Canada puts into instrumentation. So they're doing really well, and hopefully the government steps up in the next little while to fund some of these very interesting next generation instruments. My second study, Goldilocks and the red dwarfs. Goldilocks is a term for a special zone around a star where the temperature is just right for planets to have liquid water on their surface. Depending on how big and hot a star is, this Goldilocks zone moves out and away from a star. For red dwarfs, which are the most common type of star in the galaxy, the Goldilocks zone is very close to the star. Whereas for the Sun, the Earth orbits right inside that, what we would call the Goldilocks zone, because we obviously have liquid water on our surface. The current search for extraterrestrial life is targeted on rocky planets orbiting red dwarf stars, mainly because they're so numerous. Many planets, and at least one Earth-sized planet, have been located in this zone surrounding red dwarf stars. The problem that astronomers have come up with is that all stars are nuclear explosions, roughly a million times the size of the Earth. And when you go outside to get a suntan, you're basking in the radioactive glow of a huge nuclear explosion. And these things are giving off radioactive particles. It's called a solar wind. And these particles strip away the atmosphere of a planet that's not protected by a magnetic field. And it just happens that red dwarfs are particularly active in terms of their stellar wind and their magnetic fields. So astronomers have done magnetic thermodynamic type of three-dimensional simulations, and what they found is that if the Earth were orbiting in close to a, oops, I hit the wrong button. If the Earth were orbiting in close to a red dwarf here, the actual stellar wind would rip the atmosphere away from the planet. And over time, there would probably not be any life there. So although astronomers have been thinking it's very likely that there's a lot of life-supporting planets because there's so many red dwarfs and there's so many planets, it may be that these environments are maybe not so good for life as we had at once thought. So an interesting development in terms of our understanding of where life might be found. And maybe we are maybe a little bit lucky here on Earth to be around a slightly bigger star and slightly further out. Thank you.
Thank you, Al. The next subject is one that's interested me, fascinated me since I learned about it about 5-6 years ago. It's something that I didn't expect. If you ask most people what comes to mind when they think of Saturn, well, obviously the first thing that most people think of are the rings. Some will talk about the icy moons, but and I think very, very few will talk about that funny, peculiar, I should say, shaped cloud pattern on the top of on the North Pole of Saturn. Frank Marshall here is going to talk about that, as I did earlier, share his research into the origin of this odd-shaped cloud pattern and how it can persist over time. Thanks to Frank from taking I wouldn't say a break. He's doing this over on top of his master's. That's in the he's right in the thick of his thesis. So I really appreciate it, Frank. So welcome, Frank Marshall. Thanks.
Thanks a lot, Mike. So, having seen a presentation from Simon Hanmer in which we saw far more hexagons than I think any of us in the audience were comfortable with, I decided to make a presentation about hexagons. So, so I'll talk about some very interesting processes that might lead to this actual formation on Saturn, and it is a really remarkable feature which I think is up there with the red spot of Jupiter. So next slide, please. So first I'll describe how we discovered this thing. This is a fairly recent phenomenon that we only know about since 1988. Then I'll describe what the hexagon is, and I'll describe a few mechanisms that we think might be responsible for it. But we do not have a lot of information for this type of mechanism. Because of the recent discovery and the fact that Saturn was in the dark for a large region of time after we discovered it, we don't have we are only starting to get information from the Cassini space probe about this marvelous feature. And as a result, we are still in the early stages of creating models to describe it. So there's two types of mechanisms. One is called the Rossby wave mechanism. This is a relatively theoretical model, and it's based less on experimental evidence. The one that we have more faith in at the moment might be the barotropic instability model. But again, we are still in the preliminary stages. So I'll describe these two models. And I think, so next slide, please. So it was discovered in 1988 by David A. Godfrey, an astronomer. And this hexagon has been imaged ever since, but with varying results. Just after it was discovered, there were a few years in which people could, in which the Voyager probe, which discovered it, could actually take images of this thing. But generally, Saturn has been in darkness. It's been in that particular area. And it's been in that position for quite some time now. Remember, the Saturnian year is about 27 years, I think. So we're looking at about a 30-year Earth year to represent a Saturnian year. And that means that we've had to wait an awful long time before this thing came out of the darkness. And we've had to do thermal imaging using Hubble Space Telescope. Only in 2009, with Cassini flying around this planet, did this thing become uncovered again, and not everybody expected that. We thought it might just be some giant anomaly, which, like the Neptunian white spot, might appear and disappear over time. So this was quite a remarkable thing to see, and Cassini obviously produces very nice images, high-resolution views. Next slide, please. So now that we have all of these different tools that we can use to describe this hexagon, different wavelengths of imaging and very high resolution quality images, we can start really penetrating deep and understanding what this thing is doing. However, we are still prevented from understanding it very well because it's difficult to describe where the clouds are moving. This thing is about 8% larger than the Earth. Now, if you compare that with the red spot, it's actually 10% the Earth. So this is something analogous to the size of the red spot on Jupiter and deserves as much attention. We have cloud features all around the area. You can see all these little bumps, these different circles inscribed inside of it. So these are all clouds at different depths. And these are causing us a lot of a headache because it's very difficult to describe what's going on, where they are, and what their mechanisms are. So next slide, please. So the Saturn hexagon is 70 degrees north on the planetocentric scale of Saturn. So obviously Saturn's north pole doesn't align with its rotational one in the same way that the Earth's does, for example. So it's 70 degrees north of the Saturnian North Pole. And there's also a cyclone feature in the South Pole. The difference is that the South Pole feature is not as well-defined. It's not a hexagon with that kind of well-defined contour. We also have made some simulations of the clouds on the hexagon. So using simulations and using using the way that the clouds produce shadows, we can actually base on those where we think the clouds are relative in terms of relative altitude in the atmosphere. We've used simulations to work out that we think that there could be thick clouds in there, or there could be two layers of cloud superimposed on top of each other, and that these thick cloud layers are the dominant ones that we are tracking in this hexagon when we say that it is spinning around. So we don't know a lot about the clouds, but we've got some idea from simulations at the moment and based on the Cassini instruments. And as you will find later in the presentation, clouds are very important because they are a marker of whether the flow is barotropic, which means that it is independent of altitude. So there are two methods to describe this. One is a Rossby wave method. We think a vortex might be responsible for it. And the second mechanism for the hexagon is that the vortices are actually created by barotropic instability. So it's a question of the chicken and the egg. Did the vortices produce it, or were they created by it? Next slide, please. So we know from these studies of the clouds, we have an idea that we can go all the way down to the 2 to 4 bar level of Saturn and say this is where the hexagon is mainly centralized. This is where we think it occurs. So this occurs just above the stratosphere. Next slide, please. And I'll now describe the two different models that we have to describe this. The first is the Rossby wave model. It's been around for quite some time now. Allison and all proposed, I think it was early 90s, and it's been entrenched in our belief about how this thing works. With the new information of Cassini, the Rossby wave model may no longer be applicable. Next slide, please. So whenever we consider something gigantic on a planet and rotating, and we know it's a storm system of some kind, we have to consider the Coriolis force. Now, the Earth is the best example because we live on it and we know how it works to some extent. The Coriolis force is if you are standing on the Earth, you are always rotating. Because we are always standing on a rotating frame of reference, we have this extra energy associated with us compared to everything else, including the atmosphere above us. So if the atmosphere is moving at a different rate than we are, we see funny effects of the atmosphere, which are none other than the effects of us standing on a rotating frame of reference. So the Coriolis force says that if I'm standing at the top, So if I'm standing over here and I'm rotating with the Earth, then I see that if I shoot a cannonball in a straight line, from my point of view, the cannonball will appear to curve from where I shot it. And this is if I do it over a great distance, obviously, because if I do it just over a short distance, you won't notice this effect. So the cannonball will appear to curve, and that's not because it's actually curving, it's because I'm turning. So in order for me to shoot it this distance over to here where I wanted it to go, I need to apply an extra force to account for the fact that I've got this extra rotational energy which is driving me away from my target. Next slide, please. So how does this work for Earth? Well, now we're closing in to that point. So the Coriolis force has an effect on a rotating homogeneous fluid. If I drop dye inside rotating water, spinning at an angular velocity of omega, that dye will drop because of gravity, and it will have relatively no impact on the water around it. What I'll see is the influence of the water as it's rotating over the whole vertical depth. What you can see here is that the dye will diffuse, it will spread out, and as it spreads out and it falls, you'll see it form columns, which means that the water along any height will be rotating the same way. This is called barotropic flow. It's an independence of the movement of the flowing medium to the height position in the rotating frame of reference. So this is how Earth's atmosphere actually works. It's this independence of over altitude, and and air masses actually follow this movement. They tend to go along these particular paths, and you see that all the air between point A and point B will travel in the same way. So next slide, please. So how does that apply to Earth now? Well, I'm rotating on a reference frame. So this is like 2 slides ago. And now, instead of shooting a cannon over here, I look at what happens if something's coming towards me. So in this case, we're looking at a cold region in the North Pole, and the air over here will want to go to the hot air over here. That's normal. That's what you want. Normally, you'd want to see cold air flowing here, and you would see hot air going that way. So this is a normal process. But from our point of view, the air masses will actually move in a curved trajectory because I'm turning with respect to the air. This is called the Coriolis effect, and it is responsible for things like cyclones and something which is much more interesting, which I will describe in a moment. Next slide, please. Now, the Coriolis effect is basically this fictitious force that we see on things that are falling away over different latitudes because we are turning. So it's a fictitious force. We think something's moving, but it's actually us that's doing the moving. Now, in this case, the Coriolis effect has a different, if you look at something that's moving around here, it will move in the same amount of time to do a full rotation as something down here. So latitude doesn't have an impact on how fast it takes us to go from point A and return to point A. What does change, though, is that because I have to travel a further distance, 2 pi r down here, than I do in this great circle, it means that I'm going faster up here with my tangential velocity than I am down here. I'm going faster down here than I am up here in terms of my tangential speed. So my Coriolis effect will be different down here than it is up here. A gradient in the Coriolis effect means that you actually produce a wave feature in a moving jet stream. So here we have a jet stream. It's where a front occurs. You have a lot of temperature. You have a lot of pressure variation. And this pressure variation over here, if you introduce a Coriolis effect to it, you produce something called a Rossby wave. You produce a wave feature around the pole. So this wave feature propagates about the jet stream. And because it propagates, it starts to deform the appearance of the jet. So this is an actual stable structure, and it is something not far away from the hexagon we see on Saturn. And we represent this by something called a Rossby wave. So next slide, please. So this is another picture of the Rossby wave that goes around the Earth. And it is largely because of two factors. One is that we have this movement based on the different levels of pressure. We have cold air up here and warm air down here. But we also have that the air doesn't go straight from here to here or here to here. It doesn't work that way. It's actually moving along particular lines. And this is because of the Coriolis effect. So next slide, please. So now I apply the Rossby wave model to the Saturn storm system. So here you have a jet stream, like we do on our pole. And here we see that we can actually represent what's going on around the jet stream by a Rossby wave. And the whole point of what causes a Rossby wave is to do with some kind of mechanism that starts it off. On the Earth, it tends to be some transport of air masses. In this case, we think that it was caused by some kind of vortex south of it. And the vortex is something like what you see in the middle here. It's this curled region of space. It's a circular flow. It's confined in its closed loop. So next slide, please. So a vortex can be formed, for example, with a tornado. You have the circulation, and it's a closed loop, and it forms a stable structure. So that's a vortex. And here's what we think is causing the hexagon pattern on that pole of Saturn. So we think that there's this vortex here causing an instability in the jet stream. That undulation is propagating a Rossby wave. Next slide, please. So here's a close-up of the vortex that we think is responsible for it. There's just one problem with this idea of the vortex, is that we don't know where the cloud layers are that we're tracking in terms of the movement of this thing. So we don't know where particular layers are moving in the Saturn storm system. Because we don't know this for sure, and because we don't know that the Saturn storm is actually following the rotation of the planet constantly, there's a problem with deciding that the vortex is actually producing the large disturbance that we see. So a bigger, simpler problem for you to understand is if we have a vortex and we think it is generating this massive storm on Saturn, why do we now have evidence that tells us that this might be a completely different vortex to the one that we saw in 1988? That's a major argument. There's not an absolute answer to it, but it seems that there is now a large amount of doubt that this vortex has been there all of the last 25, 26 years. So next slide, please. So now we have a doubt about the vortex hypothesis. And if we don't have a vortex, you don't have that thing that can create an undulation, and the whole Rossby wave analysis is less clear. So now I was talking about this thing called barotropic flow. So barotropic flow is just, here's a mass, and it's flowing in a particular direction, and the whole of that mass is doing the same thing from top to bottom. So the second theory is stating that you can actually represent what is causing the hexagon by something called a barotropic instability. So a barotropic instability, it's if you have a barotropically stable system, you've got this vertical column, and it just moves along a particular streamline. Now, in the case of Saturn, you have these large zones of these bands, and you have these zones. And along these bands and zones, which are moving in different directions, you actually have potential for creating something like a jet stream, or potential for creating things called currents. So these are transportations of air mass. Because we are transporting air mass inside these confined regions, and because there is a vertical shear, there's a little bit of a difference between how much is being rotated this way and how much is being rotated from underneath. Our idea of the flow along a streamline being perfect breaks down, and we cannot represent this using a simple Rossby wave. We have to use something a bit more complicated than that. So this is called barotropic instability. It's because it means that if I have two zones together, one zone is dragging the middle bit more than the other zone, and then the middle bit is feeling this force, and this disrupts how the Coriolis force works on it. So next slide, please. So barotropic instability works like this. I have a current, and the current is acting the same way from top to bottom. So the current's actually going like this. Now, initially you don't see these little circles here, which are called vortices, like a tornado that I showed before. These curls aren't there, you just see a flow. The problem with this flow method is that if you start to produce a disturbance to a normal flow, like in a particular current, by say rotating the top of the current different, the top of the flow different to the bottom of the flow. As soon as you start distorting that flow motion, you can actually produce a wave. It's quite similar to a Rossby wave. And that wave, that disturbance that you're imposing on that initial flow, can become consistent, and it can start producing little circles in it called vortices. And this is actually a very straightforward thing to experiment, as it turns out, and has a well-defined physical description for why we think this works. We describe waves, which are disruptions which are disturbances to that original flow by things called wave functions. And the wave functions, which just describe normal waves, they have associated with them something called a wave number. So this is a measure of the frequency of the wave. It's a measure of how many bumps you have, how many disturbances you see over a certain amount of space. So now with this particular feature, you actually find, using the experimental model, that this distortion is caused when you're rotating the fluid at a particular rate, applying a Coriolis effect, then warping the top bit of the flow, and then waiting until different vortices are produced. And we say that the wave number for this is m equals 6. It means that we have about 6 different disturbances per cycle. And apparently, when you produce such a barotropic instability, once you produce this particular type of distortion of the flow in the current, you can produce vortices like you see on Saturn, and you can, in that particular hexagon, and you can see a stability in the structure and the stability in the wave and the vortices, because they are drawing it from that rotating force that you're applying to the original fluid. So that's a complicated thing, and I want to show you a video of it to put it in perspective. So here's an original flow, and now I'm applying a little bit of a flow on top of it. So this thing is actually rotating, and now I've got this rotating annulus put on top, and the annulus is disrupting the original flow. And this is producing something called barotropic instability, because the actual flow is now becoming hugely distorted, and you're not getting this nice kind of Rossby wave that we get on Earth. You're getting this distorted-looking wave in which it is stable, but you've got all sorts of things going on that you don't have on the Earth polar jet. And what's interesting about this particular mechanism of forming a wave is that once you have the right conditions, you can actually form a hexagon. So it's a very complicated description, but it all comes from the fact that on Saturn, we think that there was some kind of difference between one zone and another zone. Those that created a particular shear on the flow in between, and that shear started to create a wave disturbance, which has a characteristic that it can start looping around in localized areas and can start forming something structured like a hexagon. So next slide, please. So at the moment, we have two theories. We have this idea that they're both involving barotropic flow. They both assume that we have these big air masses that are moving, and they're moving in tandem from top to bottom. We have this idea that one model is a Rossby model, that you have this gradient of the Coriolis force. You have a change from the Coriolis force from the bottom to the top, and in a particular region, that change is such that you can form a stable structure, which is like a hexagon, like on Earth. And then we have model 2, which is the barotropic instability model. And there we have this idea that the vortices aren't actually driving the thing, they're actually being produced by the thing. So we are rather uncertain about which of these is actually producing it, because we do not have enough data and not enough experiments to back up that particular data. But we think we have a good idea that regardless of what is the mechanism, we can replicate it more or less on Earth and help to understand it in terms of Earth processes. This is not a particularly special phenomenon, but it might have its own unique characteristics. So next slide, please. Thank you very much.
Thank you, Frank. Frank, you're very brave for taking this on. It was certainly not an easy subject, so kudos to you for this. We have actually about 2 minutes for questions or any comments. Does anyone have anything? Glenn, I can see you. And really loud, Glenn.
Yeah, I'm still not completely clear on which of the forms of shear that you're referring to. Is it vertical shear or horizontal shear, which is the dominant?
I understand it to be a horizontal shear. So if you deal with a coordinate system that has the spherical coordinate system, you have the radius, and then you have the two angular coordinates as well. So if I take the polar coordinate and I see what the difference is between zone 1 and zone 2, so for example, here and here, you can actually see that there's a jet stream, and in that jet stream, there can be the flow will be disturbed by that and by that. And that will create a distortion in that flow, which will produce a wave propagation. In that wave, you get vortices. And in that wave, you can also see something which is more organized and structured, which is the case when we see usual wave phenomenon. You can actually produce these stable, energy-efficient, organized structures. Is that useful?
Somewhat, I guess. At least, yeah, we know now that it's mostly the horizontal shear which is doing it. I'm just wondering, why is it important that we have a barotropic flow where we have essentially constant wind velocity through a great range of height in the atmosphere? Couldn't you still have these conditions where, say, with height, you have a uniform increase in the flow speed, kind of like we have on Earth with many air masses? We end up with a fairly significant difference in wind speed with altitude, and yet we still have the jet streams forming along this line here. Does it have to be barotropic in the vertical?
I think to create, the method is proposing that you have to have this barotropic instability to produce what it got in the experimental frame that they used. So they used a barotropic instability. The reason we deal with barotropic here is because they're comparing it. You're saying that the Earth model, the jet stream, isn't entirely barotropic. Is that what you're saying?
Well, the jet stream, of course, is a ribbon of high velocity air where there's a strong temperature gradient where the two air masses at altitude are transitioning. So you have a very rapid change in the flow speed with height in a very flattened, narrow ribbon. But the air masses themselves, north and south of the jet stream, you'll end up with conditions where it's not really barotropic necessarily. You can have wind speeds changing.
Oh, okay. So you're talking about the other two positions, like on either side of it?
Yes.
Okay. In that case, you have it's all about pressure in this case. So in the jet stream, the pressure is very high. In those two areas, they're not very high. So in that condensed region, I think you consider barotropic flow. And I think on the other sides you don't, but they don't tend to mingle in any way. I think it's all about the jet because you need a particular pressure level to induce those conditions. The problem with dealing with a model like this is that the experiment I talked about was pretty simple, but they don't have a great understanding of all the mechanisms going on there because we've got this recent data. So they're saying, here's a model that we have, we put certain conditions on it, we can reproduce this hexagon.
Okay.
But we don't, it's a rather idealized condition.
Yes, certainly, yeah.
And it's not anywhere near the final answer, so we're still in a mystery, but it's saying that there is an equally valid argument to the vortex theory.
Okay, thank you.
Yeah, sorry about that. Sorry I couldn't answer it better.
Okay, this will have to be a real quick question, just over here.
Yeah, is there anything like this on Jupiter or some of the other gas giants at all?
Okay, so 2 slides down, I think, or maybe 3. Here we go, yeah. So on Jupiter, we have the Great Red Spot. This is formed because you have, I believe it's because you have some kind of shear going on between 2 different zones and a particular wave. And then that can actually produce some kind of wave pattern that can be maintained for a particular period of time. So this is based on the Coriolis effect and this wave stability model. But I don't exactly know the features of Jupiter. And like I said before, there is this thing on the Earth at the top, which is this Rossby wave. And and there's something on Venus as well. There's a giant cyclone there, but I don't know much about that one. Is that okay?
Yeah.
All right, that'll have to be it.
Okay, I'll answer questions at the break if people have some. Yeah. Thanks a lot for listening.
Thanks again, Frank. What a tough subject to take on. Next up, before our break, Stefan is going to give us an update on his recent work with Astro Pontiac.
Thanks very much, everybody. Most of you have probably seen me once, maybe even twice. I'm the president of the astropontiac.ca, the Pontiac Quebec Observatory Initiative. And what we've done something quite exciting. We've just launched a crowdfunding campaign. And for this, some members of the RASC helped us out. And we did a wonderful solar observing session on June 15th, and we put together a quick video of that day, and also trying to tell our story of our campaign. So we used that video to head our campaign on Indiegogo, and I've been pounding the pavement trying to get some attention. Here's an article that came from the Ottawa Citizen. Also, we've been featured on News 1310 as well as the Aylmer Bulletin. And this morning I was on CKCU. This article helped us get a big step towards the campaign goal itself. We still have a long way to go, but within 24 hours of this article hitting the presses, we had garnered an extra $1,000 towards our $12,500 goal. And this is our current total. We've got $2,005 raised of the $12,500 goal, and you may wonder what is driving this. For the crowdfunding, it's a wonderful way for a group that is a not-for-profit like us to be able to say, we can't offer receipts, and we're not a private corporation, so we can't really do investments. We can offer perks for people who decide that they would like to support us. So our perks start at $5, and that's the price of maybe 2 evenings of RASC meetings parking, and they run up a little bit higher than that. For $5, there's a little postcard with some astrophotography as a thank you. For $10, you could get the same and come to one of our events, like a presentation on astronomy, one of our community engagement. I'll tell you some more about those, but a little bit further up the scale, we have a special thank you from Mark Garneau, who was very kind to support us with signing some certificates of thanks. And when the article came out in the Citizen, he retweeted it. I'm shamelessly plugging this. A wonderful idea and a worthwhile project for those who want to let their imaginations soar. So you may wonder, with a place like Nirvana that RASC members can go to, why you would be interested in a place that's just 40 minutes away from the city. And the answer is family, and also people who aren't as heavily into the hobby, but could really benefit from seeing the difference that a cloudless country sky can offer. So I won't take up too much more time of this forum, but if I have my table out front and I'm giving cards away, and if you could support with any amount, that would really be helpful. Every contribution is rewarded in some way if that's the path that you choose. And I think that there's something for everybody. Thank you very much.
Thanks, Stefan. Again, Stefan's been working on this tirelessly, as you know, for my gosh, several years here. Is not giving up. This will benefit all of us in the National Capital Region, not just those people in the room here, but all of us. So if you can, please help them. Okay, just before we break here, I wanted to say a couple of things for those people who are maybe here for the first time tonight. Let's talk a little bit about membership in the RASC. One of the things we have, and I'd like to talk maybe a little bit on different things from meeting to meeting here. One thing that maybe should get more press is the Ted Bean Loan Library. From time to time, we get telescopes that are donated to us. Just recently, Al Scott mentioned there was a 10-inch DOP that was donated to us. And it just adds to our loan library. So much like a book, you can sign out a telescope and try it. If you Google Ted Bean Loan Library, you'll find it on the web, and you can see what telescopes are available. Al Scott is running the program now. If Al, can you just raise your arm up right now? So if anybody wants to see Al during the break and inquire more about it, he can tell you. As well, we of course have our own observatory just in the Elmont area, Fred Lossing Observatory. Next slide, please. Membership also brings you a number of journals and some literature. Sky News, Canada's astronomy magazine, is included with it. Next slide. We're going to have our break now, but before we go to our break, see this box here? This box contains the raffle tickets, the word I was struggling with earlier. That raffle ticket box has gone missing. So Oh, it's in the sound room. Ah, so it was me who left it. Okay. So, okay, our next presentation is with Richard Alexandrovich. Richard, as you know, when he's done presentations in the past, he's very thorough. He researches his presentations much like Frank Marshall, very, very thoroughly. You'll see that tonight. He's looked ahead at the Kepler mission and what's next with it, and our quest to find planets in other solar systems. So please welcome Richard Alexandrovich.
Good evening. Good evening, everyone. Glad to be back again. I'm basically covering an area that's been quite popular in the field of astronomy, and it's garnering quite a lot of attention. And it's an exciting field. It's relatively new. Started in the mid-90s. So I'll basically cover what's going on with a little bit of history, a bit of Kepler data, what's happening to Kepler. And I think I'm going to, because of time constraints, I'm going to cut this presentation short and have like part 2 and 3 later on. What's the forward? Right hand? Right. Okay. Okay, so the idea of worlds beyond our solar system has been tossed and bantered around, in case you didn't know, for centuries. Around 1600, it was Giordano Bruno who postulated their existence and was burnt at the stake for his beliefs about planets and having people on those planets. So you can see it goes on quite back in history. And then Epicurus, I got it the other way around. This one is Giordano Bruno. Epicurus was the one before it. Epicurus, around 300 BC, stated that Epicurus of Samos stated that with his simplistic views of the universe, there are infinite worlds. I'll just go back. There are infinite worlds, both like and unlike our world of ours. So he believed that there were more worlds than just one of this Earth. And of course, that's Giordano Bruno, who was burnt at the stake for his beliefs, because it was heresy, considered heresy back then. And then in 1952, one of the prominent astrophysicists of the time, his name is Otto Struve, postulated that there are planets around distant suns, and they can be detected from Earth. You have to remember, back in '52, they didn't have all this high-tech stuff of lensing, micro-lensing, and transiting, and radial velocity technique. Back then, a lot of the astronomers, his peers, thought that he had a few broken toys in his attic, but actually, during that time or later, he was actually bang on right. So as far as discoveries, in 1992, they used pulsar timings, astronomers, and they detected at least 2 planets and a third candidate, a third possible planet, around a pulsar corpse, or a corpse of a dead star, and it was the least likely of all places to find such of these planetary mass bodies. In 1995, 2 Swiss astronomers discovered a hot gas giant orbiting a sun-like star in Pegasus, romantically tagged Peg 51. And those were Michael Mayer and Didier Queloz of the Geneva Observatory. Its speed was 300,000 miles per hour around the host star, which is just in 4.2 days. And it is only 4.6 million miles from its host star. Mercury, by comparison, is 58 million miles, and that's where you can see 51 there around the circle. If you're looking at it, it's a 5th magnitude star. It's easily visible in backyard scopes. It's a sun-like star. And in 1998, the first low-mass planet near the galactic center was discovered by microlensing, whereby the object here lenses, or actually the mass of the planet and the sun and the star lenses a more distant star, thereby creating more information and data regarding these 2 bodies in question. So the foreground star's light is actually enhanced by about 10 times and then focused to give you information and data on the planet and star in question, and of course the Earth here. So this is all happening in terms of gravity and perhaps even dark matter. The first transit was in 1999 of a transit of a planet going across its host star. It's a very basic, simple technique whereby the planet crosses the face of the host star and it dims the light, and this is a function of brightness versus time. This was a technique that is used quite often. And then well into the 90s, the floodgates had opened, and there was, of course, a surge of excitement and intrigue, and it rejuvenated the astronomical community regarding the search for alien worlds around these distant stars. The main, participant or the main contributor back in the 90s was Lick Observatory. Initially, they were made by ground-based observatories, such as the one here, Lick, atop Mount Hamilton in Northern California. But astronomers will continue to use these ground-based scopes in the future as technology and sensitivity improve, such as adaptive optics. And then the search campaign shifted into space. Here, the advantages were that they wouldn't be hampered by turbulence of the Earth's atmosphere, seasonal cycles, and of course, diurnal interruptions. So space does have advantages, except it's a little bit more costly. And as Al Scott alluded earlier, there's the MOST Space Telescope with the chief prime principal investigator, and Jamie, and he's a funny guy, actually. He did a talk here a few years ago. It was entirely designed and built in Canada, and its primary task was to study seismic pulsations in stars that were lying beyond our solar system. And looking at these vibrations will also tell scientists that about the internal structure of the star, including its size, mass, and makeup. The size is about the size of a large suitcase, which is about 54 kilograms, about the same weight as I am. So now you know something personal about me. The scope is only 15 centimeters in diameter, so a backyard scope is probably larger in some cases. It's a very small scope. And something the Americans really hate us talking about is that it's 10 times more sensitive than the Hubble Space Telescope in detecting tiny changes in a star's luminosity, which is its primary objective. The first big discovery was the star Procyon, which is quite evident in the winter sky, not too far from Orion. It showed that Procyon, a first magnitude star near Orion, shows no pulsations at all, contrary to 20 years of theory that it was a variable star. And then in 2005, they discovered a large planet that orbited so close to the star that the star was forced to rotate in sync with the planet itself. Normally it's the other way around. So the planet had so much mass, and because it was so close, it caused the star to rotate in sync with the planet. It was gravitationally locked in like the moon is to the Earth's orbit. And then enter COROT, which stands for Convection, Rotation, and Transit Satellite, which was manufactured and put up into space by the European Space Agency. It basically is similar to the MOST telescope. It has high precision photometry to study the pulsations of stars, which, by the way, is called asteroseismology, and is similar to MOST in some respects. And also, it was looking for the search for transiting planets around main sequence stars, that is, stars that are burning in their main hydrogen burning phase. Its orbit was about 900 kilometers in a polar altitude, which had the inclination of roughly 90 degrees. The scope was a little bit larger, 27 centimeters in diameter, and its field of view, it was rather restricted to two areas. One near the galactic center, I believe it was right here, and this is the anti-center, which were referred to as the COROT eyes, which is about 10 degrees in diameter. So as you can see, there was all this space that was being missed out on. But as I will mention later on, not tonight, that the future observatories are going to look at millions of stars, literally millions, hundreds of thousands, and Kepler will just be sort of a little thing of the past. So again, COROT was observing seismology in stars and transiting exoplanets, which was the main method during that time. So as the search methods became more sensitive, planets slightly larger than ours and even smaller will be detectable using a variety of methods. One of the main ones is the Doppler method, or the radial velocity, where they use the Doppler shift. Basically, the star, when the planet moves around the star, it sort of tugs at the star moves forward, and then as it comes toward Earth, it's redshifted, and the star moves backwards. So this is one of the methods. It's not the main method, but one of them used back in the 1990s. It's a very simple approach. And then enter Kepler. Well, as we all know, Kepler had its share of problems. It was launched in 2009. Its primary mandate was to look for Earth-sized worlds around G-type stars, stars similar to our sun, specifically in the habitable zone. But it is not a search for life nor even signs of life, so we have to get that straight, because some people were assuming that Kepler was going to look for life, but actually it's looking for planets that mimic Earth, or at least Earth analogs. So far they haven't found one yet. So the Kepler mission is to give us a better understanding of how our solar system is and how it compares to other stellar systems. When planet hunting was in its infancies, astronomers assumed that the stellar or solar systems outside ours would be similar to ours, but they were in for one hell of a surprise. Over 20 years of surveys, which includes Kepler, we can now say that there are many planetary systems, if not all, that do not mimic ours. But astronomers are confident that they will find something similar, where there are terrestrial planets closer in and then the gas giants further out. So it's just a matter of migration. The planets probably formed close to their stars and migrated outwards. So we are seeing a lot of these extrasolar systems that are in their infancy. So we're seeing them in different epochs of time. But there are some similarities about these stellar systems. One planet with a density similar to Earth, that they have confirmed, because they are candidate planets, so the candidates have to be perused over a few times before they can confidentially say that it's the right theory. They found terrestrial rocky planets in the habitable zone of their star, and 200 systems having multiple worlds. So here's a simplified graph of what the Kepler planet candidates are up to about January. And you can see by the color codes, which color is very important, the Earth-sized planets. There's not too many. There's a lot of the Neptune-sized worlds. There's quite a few super Earths, but Earth-sized, as the techniques become more sensitive, the resolution will be better, and there'll be more of these blue dots in years to come. So what Kepler has told us is that a lot of tantalizing clues are out there about worlds that could potentially support life. Astronomers estimate that they will probably, well, in our galaxy, I don't think they'll find all of these amounts, but 8.8 billion Earth-type worlds in the habitable zone of their stars. So that's a lot of worlds, which increases the possibility of having conditions that are conducive to life. And of course, it'll be up to the future missions that will be the arbiter of these statements, whether they find an Earth and whether there's an atmosphere, and that's not too far ahead. At this present time, however, Kepler is running on borrowed time. So the mission scientists at NASA had to come up with something to sort of have the Kepler probe hobbling through space. I guess if you've been keeping up to date on the Kepler data, the three of the star trackers are not working. There's two of them here to show. You need at least two star trackers to point the scope in the proper direction. Actually, you need three wheels for precise pointing at the star. Sorry about that. And as of late January 2014, Kepler has bagged about 3,500 candidate targets, Earth-sized worlds, of which 242 were confirmed. That's one half of its data. Then there's the other half that awaits processing for astronomers to find out, and that's going to take anywhere from 18 months to 2 years before we get all that data in. So the conclusion is that worlds are commonplace around other stars, and their sizes are very widespread. So the methodology here is to use the sun to keep Kepler in a sort of stable orbit as it looks for planets. The radiation from the sun will be on Kepler's back. It'll be in an orbit that will be parallel to the orbit of the sun, and there'll be different campaigns, of course. So the sun's radiation will keep these the gyros or the wheels balanced, and hopefully this will keep Kepler pointing in a more or less proper orientation. However, the resolution won't be as good. It will only be about 300 parts per million in terms of sensitivity of resolution, as opposed to 30 parts per million, which was seen on the healthy Kepler. Now, even if K2, which is the new resurrected version of Kepler, fails to yield robust data, scientists are optimistic that the unprocessed data from the memory banks, the other half, will provide intriguing information about hundreds of planets that are near the star's habitable zone. And as again, like Al was mentioning before, we're probably going to have to reconsider what is meant by the habitable zone, because, as you know, Jupiter and Europa, there are a lot of theories that there could be life around Jupiter and Europa, and they are well beyond the habitable zone as far as our solar system is concerned. So if there's something swimming in the salty oceans of Europa, then we can say, wow, there's a revelation in science. And even if there isn't, it means that life, we're rather lucky to be here, because life is very rare, extremely rare, but that'll come in time. So the search for life will be a long one, and it'll be a methodical process, and of course will have to take place in several phases from preceding campaigns that will lead on to more ambitious campaigns. So I would say by the mid-2020s, 2024, scientists are optimistic that the precursors to life will be detected via the biomolecular spectral signatures in the atmosphere of a particular planet. As a matter of fact, this was just hot off the press, well, a few months ago. The atmosphere of Tau Boötes b, which is a 5 Jupiter mass body around Tau Boötes, has water molecules in its atmosphere. So they are able to detect these biomolecular signatures. And but the thing is, it's only 5% the Earth-Sun distance from the star, so it's extremely hot. So they will be considering to study atmospheres, and this is where the James Webb Space Telescope comes in, and the new one in Cerrero, I believe in the Atacama Desert in Chile. It's going to be a 39-meter telescope that will be built in about 7 years. They will be able to directly image these planets and be able to collect spectral signatures from the atmosphere itself, which I find rather amazing, considering that these planets are hundreds of light years from the Earth. So that's about it. And if you have any questions.
In the interest of time here, and to finish the program, if people have any questions or anything you want to discuss with Richard, if you could do that after the break, after the meeting, that'd be great. Thank you, Richard. Okay. Very much appreciated. Well done.
Go ahead.
Okay, next up is Glenn LeDrew. As you know, Glenn has been involved in designing and assembling telescopes and been involved with the optics for many years. He's clearly the person to speak to this subject here, optical aberrations that we see in telescopes. Glenn?
Looks like we have a little clipping on the slides here. The URL at the bottom that's chopped off, that's where I got the great majority of the illustrations here. It's a nice little introduction to optical aberrations. If you want to follow up more, you can even just do a search on, say, optical aberrations illustrated. But the URL, it's www.handprint.com/astro. Astro is in caps.
and then AE4.html. Anyway, a search would bring that up, and you'll find these illustrations and text, which I think are a fairly good way to start. Now, several years ago, Peter Cervolo passed on to me something that I think someone had told him, which is a very apt comment, and that is that astronomers look into an eyepiece and see an image, whereas opticians look into an eyepiece and see aberrations. And since I've got involved in optics a little more heavily in the past few years, I realize that's very, very true. Now, what we want to see ideally when we look into an optical system at high magnification is something like this. A very nice, clean diffraction pattern or Fresnel pattern. In the middle is the bright airy disk where some 84% of the light should be concentrated if it's an unobstructed system, surrounded by 2 or more nice round diffraction rings. You'll notice here that we see a nice colorful rainbow-like effect. This is not chromatic aberration, like the color error you see in basic refracting type telescopes. This is actually due to the wave nature of light. The longer wavelengths, the red colors, they are diffracted at larger angles than the shorter blue wavelengths, and therefore we see a red fringing on the outer edges of the diffraction rings with blue fringing on the inside. Just wanted to stress that that's not chromatic aberration, that's actually the action of light itself. Here is an illustration which kind of shows what we look for with an optical element or a system which is aberration-free. All of the light rays passing through and brought to a focus over here, they all appear to come from a spherical wavefront which converges toward that point. Or in reverse, think of it, if you're having a pulse of energy emitted from a point, it would emerge as a spherical wavefront. So we're just getting that in reverse. That's an aberration-free system. There are several aberrations of different forms that plague optical systems, and we can classify them in 2 broad classes: errors of focus and errors of magnification. Errors of focus cause general blurring of an image point. Errors of magnification cause things like elongations of image points, or even overall distortion of an image that changes the scale as we change the field angle. There is one aberration which actually is a very difficult one to correct for, astigmatism, which is a kind of a combination of an error in focus and magnification. There are 2 aberrations which are related to color, and that is the chromatic aberration. One is called longitudinal, which means that you have a change in the image with along the optical axis, and then lateral chromatic aberration, which causes a kind of a prismatic spreading out of color for an image point. The others, they affect all wavelengths more or less equally. So first we start off with chromatic aberration, which is the aberration that was most bothersome to our early telescope users and resulted in extremely long telescopes of tens of feet or many meters in length, with very long F ratios of F100 and longer when they're using these simple singlet lenses. And we see that, I should point out first of all, the colors here are not representing the color of light or wavelength, but rather just the position of where the rays are passing through the optic. So with the usual form of spherical aberration, the undercorrected variety, with usual spherical optics, light rays passing through the center of the system are brought to a focus at some particular distance, but then light rays which pass through ever farther from the center, closer and closer toward the edge, they are brought to a focus nearer to the optic than are the rays brought to a focus from the center. And that causes an overall blurring. You can't really find one perfect focus. If you're inside focus, you'll end up with an image that is sort of dimmer in the middle with a brighter ring. Outside of focus, we have a brighter center with a large diffuse halo of light, and then somewhere in between we have a more tight configuration, but there's two places where we might settle on focus. One is called the circle of least confusion, which is the tiniest blob. And then there is best focus, where we have a tight core surrounded by a small halo of light. That's where we tend to naturally focus. But with spherical aberration, there's always a bit of a blurring, never a good, clean, tight spot. And here we can see graphically shown the two forms of spherical aberration, undercorrected versus overcorrected. I just described undercorrected, and overcorrected is the opposite, whereby the center rays are coming to focus farther away, or I'm sorry, closer, and the outer rays are brought to a focus farther away. It's a kind of a minor distinction. Usually undercorrected spherical aberration is what's usually encountered. And just a very crude simulated view where we have the spherical aberration causing something of a focused point surrounded by a small fuzzy halo of unfocused light. I'm just wondering if something got a little out of sync here. No, it hasn't. Anyway, so here we have chromatic aberration, the longitudinal chromatic aberration, where different wavelengths are brought to focus at different points. A lens, it acts much like a prism, where the blue light is refracted more strongly than the red light. And so we find that in the outer parts of the lens, where the wedge shape of the glass acts like a prism, the blue is brought to a focus closer to the lens, and the ever longer wavelengths are brought to a focus farther and farther away. And across the full visual spectrum that our eye is sensitive to, from violet to red, this entire range is called the secondary spectrum. At best focus, you'll end up with a more or less whitish image of a white point surrounded closely by a little bit of a yellow-green fringing, a little larger red fringe, and then an ever larger than all of them, but kind of a blue fringe. This graph, it just shows in a fashion the range in distance from the nominal focus for different types of refracting systems, undercorrected, achromatic versus an apochromatic telescope. And just for convenience, the different colors are just arranged vertically, and the optical axis is the little blue line, and the best focus, which is kind of selected for yellow light around where our eyes are more sensitive, yellow to yellow-green. And we see that for a very simple lens, the violet comes to a focus very closer to the lens, which is off to our left, and then the red somewhat outside focus. But then if we combine two different types of glass, which have different dispersions, we can make an achromatic lens, which very greatly improves things by essentially folding the secondary spectrum back on itself, and we get a much narrower range of secondary spectrum. And then with an apochromatic telescope, which is by using either the second very exotic glass type in conjunction with a more ordinary crown, or by putting in, say, a third element, then you can fold the secondary spectrum on itself to a third degree and end up with a very small range in the focal distance, which gets closer and closer to image perfection. And now the other form of chromatic aberration is lateral color. And in a nutshell, it arises because light that is entering the optical system off-axis at an angle, the refractive power of the lens is actually behaving differently for light that is on one side, we'll just call it the top, versus the bottom of the lens. And we see the red and yellow light coming to a focus, but the blue rays having a different power, and combined with the refraction, they end up passing through the optical axis at an offset position. So you end up with a little vertical smearing, where usually you'll have a bit of a red fringe closer to the optical axis and a bit of a blue fringe on the opposite side, closer to the field edge. And simulated views of the longitudinal and lateral chromatic aberration. We already saw one represented earlier with the longitudinal color error, where everywhere over the field white image points would be similarly discolored with a close a reddish fringe and then a larger violet halo. With lateral color, we end up with a radial spreading out that gets worse and worse the farther off axis you get. I've seen some lenses produce truly horrible lateral color, including a Pentax fisheye lens, which was really ghastly. It was quite a surprise to see. Another optical defect, which is pretty common in telescopes, is field curvature. And that just makes it hard to achieve focus evenly throughout the whole field of view. The more common form of curvature is positive, where I keep hitting the wrong button, I'm sorry for that, where the focal surface is curved such that it's concave toward the objective. It's not too often where you'll see negative curvature where the field is curved in the opposite sense, but that can occur, and certainly in cases where astigmatism is one of the aberrations that's being corrected for. For Newtonian telescopes, the radius of curvature of the focal surface is roughly equal to the focal length, but for Schmidt-Cassegrain telescopes, the curvature is much stronger, where that radius is only about 1/3 of the focal length. So the radius of curvature in a Cassegrain would be about here, and the curvature of the field would therefore be more extreme, which is why the coma correctors, or I'm sorry, the field flatteners, yes, for Cassegrain telescopes, well, focal reducers, they also build that in as well as another correction, especially for imaging. So with curvature field, as I mentioned, you can't get uniform focus over the entire field. If you focus sharply for the center, the outer field can blur, or vice versa. Another prevalent aberration is called coma, and users of Newtonian telescopes are intimately familiar with that, especially if they use very fast telescopes of around, well, faster than f5 anyway, and f4 it becomes pretty prominent. And this is a result of the change in the magnifying power with the light that enters off axis, where, similar to what I mentioned earlier, the light that is entering one side of the objective, it has less refractive or reflective power than light entering the other side. So the center rays, and in here it's not related to wavelength, it's just position, the red-colored rays passing through the center come to a focus at one part on the image plane, but then rays that are coming from farther away from the center, above and below, they tend to want to come toward a focus farther and farther off axis, but they're not at focus at the same time as the center rays, and so you have a whole series of ever larger overlapping blur circles, and it kind of looks like a short, stubby little comet, hence the term coma for the aberration. So the center rays produce a fairly sharp image point, and the light energy is kind of concentrated in a bit of a fan shape with a bit of faint energy filling in the rest of the blur, and it kind of looks like a little flying bird. In a reflector, you can easily see how the matter of the changing effective power occurs here. The yellow rays are showing light from an object on axis coming to focus at the center of the field. But here we have green rays for an off-axis object that is above, and the light is striking the top part of the mirror here. And the angle of incidence and reflection is larger because this curved surface is different in slope from the curvature of the surface where rays from the bottom of the light bundle strike the mirror. So you can see here the angle between the incident and emergent rays here is greater, whereas down on this side it's much smaller. So that gives a little bit of a clue as to why coma forms, because of effectively a different magnification factor across the surface of an optic. And the chromatic blur is such that on the center of the view at the optical axis, you have a nice cleanly imaged point, but at any distance off axis and getting farther and farther away, the size of the blur grows larger, and these little comet shapes become quite obvious toward the field edge. And I mentioned earlier about astigmatism being one of the bugbears of optical designers. It's very difficult to completely correct this aberration, especially for wide-angle systems and for eyepieces, which have very wide fields of view. And I'll try to be brief on this one. What we're looking at here is the focusing action of an objective in two mutually perpendicular planes, the sagittal and the tangential plane. If we look at the bottom first, we see the tangential plane, which is slicing through the lens on an angle, and the plane, it includes the optical axis as well, and we're just looking at the action at focus, say, either above or below the center of field of view as we look at the system sideways. The top view, it shows light that's entering from either below or above. We're looking down on the system, and we're seeing that what the focus is doing either above or below the optical center. In a nutshell, in the two mutual planes, the focal distance is different, and the net effect is really where we have a sort of best focus between the two extremes, which here in this illustration looks kind of like a blurry blob, but in practice it tends to look like a very compact little cross shape. The best focus in the two planes is a bit outside of this, one inside focus, one outside, where we have a more compact concentration of light, but the other perpendicular component of the aberration forms a kind of a streak of light or an elliptical shape. And as we go farther away from focus, we see these expanding out into a little bit of a slight cross shape, but the overall pattern gets larger. So with astigmatism, as you rack inside and outside of focus, you'll kind of transition for a star that has more of an elongation in one side of focus, and then it flips 90 degrees and goes perpendicular to that on the other side of focus. I think I can skip over this one here. It just shows the difference in the curvature of the tangential and sagittal focal surfaces for the aberrations compared to the Petzval surface. That's a little more in depth than we need to cover right now. So the two kinds of astigmatism, depending on which side of focus you're on, will manifest as either a radial elongation like we see on the left, with stretching away from the field center, tangential astigmatism, and sagittal astigmatism forms a kind of concentric stretching out. And this is a fairly common form of astigmatism actually in binoculars. These are slightly better illustrations of the representations of spherical aberration, coma, and astigmatism. With the usual undercorrected spherical aberration inside of focus, you end up with a weak center and a bright ring. Outside of focus, a bright center with a diffuse halo. And coma, well, we can see how the energy of all these effectively innumerable overlapping circles causes a concentration of energy at about a 60-degree fan angle. And then here we see astigmatism as we transition going through focus, where the orientation flips 90 degrees and with a bit of a cross shape in the at the best focus in between those. Below we have a higher fidelity representation of a combination of coma and astigmatism, which is a little closer to real world conditions, especially with wide angle eyepieces. And we now come to the matter of distortion. And this is not to be confused with aberration. Many people will confuse the two terms. Aberration is the action on an image point. Distortion is how the overall image scale changes with distance from the field center. So we have two examples of distortion here, where in the top view, negative distortion is such that the image actually, as you go from the field center outward, the image becomes more and more compressed. The magnification in the outer parts of the field is less than it is toward the center of the field. And so you get compression as you look out toward the field edge. And the opposite with positive distortion causes the image to become ever more stretched the farther off axis you get. So things become stretched out. Nagler eyepieces and the Ethos eyepieces are really good examples of positive distortion, where you look at a straight line and move it out toward the field edge, it will become quite curved outward. So positive distortion, where you have a radial stretching of the image in the outer fields, causes the patterns to become more expanded and stretched out with increasing distance from the center. Negative distortion, which is commonly called pincushion distortion, compression toward the outer edge occurs and causes things to look like they're getting bowed outward. So a straight line here near the field edge would curve like so, whereas with the positive distortion, or sometimes called, or actually, yeah, that's pincushion distortion. This would be barrel distortion. A straight line near the edge would bow outward like this. I'm just exaggerating that curvature here. And lastly, we come to spherical aberration of the exit pupil. This is a more recent phenomenon with ultra-wide-angle eyepieces like the Naglers and so on. And that's the result of the exit pupil forming at effectively different distances from the eye lens, depending on the angle of the light bundles emerging from the eyepiece itself. And here we see the on-axis light bundle represented by the red rays. Well, actually, there's even no focus. At mid-range distances, halfway out in the field, the exit pupil would lie a little bit closer to the eye lens, and then for the extreme edge of field light rays coming through, they would come to or meet at a common exit pupil distance even closer to the eye lens. And that means as your eye is moving about, either closer to or away from the eyepiece, or if your eye is moving about as shown in the lower field or image where you're kind of looking askance, trying to look directly at one side of the field or the other, that will cause pupil clipping, and you'll end up with effects along this line in the center panel, especially the notorious kidney beaning, where you'll get a shadow that morphs and changes shape and comes and goes, moving about the field as your eye moves about. That's the main manifestation of spherical aberration of the exit pupil, is the kidney beaning. And that concludes that presentation. Thank you for listening.
Thanks, Glenn. Outstanding. As you know, just for the next segment is the observer reports. If all of the observers who are going to be sharing their images, you could line up on the side here. We'd like to do them fairly quickly here. So, as you know, we're always trying to improve these meetings here. So one of the things we're going to do here is that before everyone leaves the room here, we're going to ask each of you to sort of fill out a little test here just to see how much of Glenn's presentation you actually followed. Okay, and so thank you very much for your cooperation, and you can't get out unless you fill it out. Joking. All right, first up is Gordon Webster.
Well, I actually followed directly behind Glenn's presentation. Okay, so I've got a whole series of things here. I've been saving them up because we haven't been getting any decent weather. This is a very quick, rough sketch of Mayor Humorous, whatever. I was hoping to be able to get back to it maybe the next night and fill it in, finish it off. But anyway, next, please. Sorry. Oh, yeah. It's an open cluster in Ophiuchus, 4.2. And it was identified by my go-to scope because it wasn't on my atlas. Next, please. We have Xi Boutius. It's 4.8 magnitude yellow primary. And I saw the 7th magnitude secondary as burgundy. It's often described as being a deep orange, but you get reports of both. But that's very close to how I saw it. Next, please. M104 was just a nice star field. I just really liked it. And there's not a whole lot of detail, but I just thought it was nice. Next, please. NGC 4565. I've seen this from my backyard in Orleans, and it's always been a small, faint, hard to see thing. I was out at the FLO back in, well, a couple months ago, in May, I guess. And I was really, really shocked at how big this was in the eyepiece. There is an error here. It wasn't with my 120 refractor, it was with my 12-inch Newtonian. Next, please. Caldwell 21, NGC 4449. It's an irregular galaxy. This was the astronomy sketch of the day back on Wednesday. Next, please. And this was just for fun. I went out to pick up the pizza one night, and I spotted, which one's the? Yeah, okay. Spotted the moon over here, and a cloud that looked very much like Pegasus to me. Okay. What I missed, I was really hoping to get it. I was shot with my cell phone. What I was really hoping to get was the airplane that was flying right across here. So, that's it. Thank you.
So, Brian, we kind of half expected that cloud one would have been a slide from you. You know that?
He stole it from me, yeah. All right, very quickly, I went on a writing retreat weekend to Pembroke, Ontario 2 weeks ago, and while I was there, I noticed at the park by the waterfront, they have a portage sundial. So you can see there's the voyageur with the canoe on his back, and you can see the star at the top. And if you go and sight along the keel, you're looking right at the North Star Polaris. So if you can see the what it says right here. Oh, that's okay. Go ahead, Chris. Thank you. So it's just saying, gives a little bit of information about it, on how a sundial works. Sunlight and moving shadows combine with a rotating Earth to reveal the passage of time. And the keel of the canoe is the sundial's gnomon, casting a shadow that displays the time as it moves across the numbered hour lines. All right, we can go to the next one, please. So here's looking at it from the other side, and I was kind of intrigued by this, so I thought I'd go up and I would sight along the keel. I wondered, is it possible to do a daytime naked eye observation of the North Star Polaris? And who knows what the answer to that is? Right, because the Polaris is a second magnitude star, and from all the reports I could see, you need about a minus one magnitude to even start to get something naked eye. If we go to the next one, please. You can tell what time I was there. 3 o'clock, 4 o'clock. There I was taking a break from my writing there. All right.
But it was daylight savings time.
It was daylight saving time. That's right. That's right. Oh yeah. So I wasn't actually taking up too much time. So that's all right. Okay, we'll go to the next one. Something I noticed at Lee Valley Lee Valley Tools is they had these shorts on sale. Shorts, 16 pockets, $75. Nice poly cotton blend. 16 pockets. Oh, yeah, okay, good for astronomy. Wait a minute, what are they called? These are Belgian made, and they're Herrick Workwear Palace shorts. Palace? Well, is that an asteroid in your pocket? Right? But I mean, there it was. I mean, if you're looking for it, they while supplies last, I guess. I don't know if they have any left, but if you're interested in something like that, I think that's it. Thank you for doing that. Thanks.
Awesome. Next up is Joe. Thanks, Brian.
Sorry. So this one is a bit of a lucky grab on that small dot there, which actually turned out to be the shadow of Io. I took this one using my 8-inch Meade LX90 and attached the camera to a Beta Planetarium Hyperion eyepiece, which those who haven't seen one, you can actually screw off the eye cup and screw on a T-ring, so you can actually attach your camera directly to the eyepiece to get a little more magnification than you might get at prime focus. And I was just shooting Jupiter, and I brought it inside to stack it, and I thought, oh rats, I got a piece of dust on somewhere in the optical train, and but the RSC observers guy straightened me out, and that's actually Io's shadow. This was also taken with the same setup with the Hyperion eyepiece. I got some nice magnification on a couple of sunspots on. This would have been June 7th. So this would be AR 2080 and 2085 for those who keep track of such things. Next image, please. Yeah, and this is actually that's the two, the lower two ones there. That's this was taken at prime focus with the same setup. I just swapped out the eyepiece for prime focus and got the entire sun in this image. It was kind of a busy sunspot day. And lastly, this was taken with my Ioptron Sky Tracker, which is a camera mount only. I used a Canon T2i with a 300 millimeter zoom lens, just a basic Canon lens. What's interesting about this one is I was really impressed. This is the first time I've actually managed to get a long exposure longer than 13 seconds, because I live in Barrhaven, and I have a street light literally 10 steps away from the setup that I did this with. And this is a stack of 6 2-minute exposures. So I used the Astronomic CLS light pollution filter, and I was really impressed with that, because if I did the same setup without the light pollution filter, I would get probably 6 or 7 seconds before I'm totally saturated with light pollution. So I was pretty pleased to get this. One thing I will throw out there is if there's far too much red in this, I color corrected by using a custom white balance after shooting a gray card, but the way the light pollution filter works, it really pushes the red when you do any kind of adjustment. So if anyone has any experience with fixing color in post-processing, I'll buy you something at Kelsey's after the meeting. Thank you.
Thank you, Joe. Paul.
How many images did you stack?
Oh, it's about 85, I think.
Okay, let's go back.
Okay. Yeah, the chime tells me that I've got to rush. So I got a few things for you there. I wanted to show you this one. I just finished processing this. Jim Maxwell and I were out at SmartScope a week and a half ago. We're still running some tests. We're getting close with it. But this was a test image of Saturn we shot on a night of not particularly good seeing. And the scope still needs collimation. But I wanted to show you this because I just want to let you know that SmartScope is happening. So stay tuned for more and better. Oh, that's the movie. Oh, I didn't know you put that in there. So this is just a combination of 87 of the best images. We grabbed about 1,500 frames there, and that's basically like a live view of Saturn as we captured it. All right, next object I have. I finally got a chance to image an object that I've wanted to for a while with my 11-inch now that I have the observatory set up, and that's M87. I'm fascinated by this object. M87 is one of the largest galaxies in the Virgo cluster of galaxies, and so a couple of months ago I managed to do a nice run on that. Next one there, Chris. So this galaxy is really quite fascinating. It's a supergiant elliptical galaxy. It has several times the mass of our own galaxy, even though the dimensions of it, the visible dimensions of it, are about the same. It's relatively featureless. There's hardly any dust in this galaxy. And by some estimates, the extended mass of this galaxy, when you look beyond what's visible there, is perhaps up to 200 times what the Milky Way is. So massive, massive galaxy. But what's really interesting is at the center. So when you play with the data, you get the next slide, and you see the core. Now, almost 100 years ago, in 1918, this jet was first identified in the core of the galaxy. And since that time, we've also identified that it's a source of extremely strong radio waves, X-rays, and gamma rays. Next one, please. So what's causing this is a supermassive black hole at the center of M87. This black hole has roughly 4 to 6 billion times the mass of the Sun. So it's a massive, massive object. And what makes it really interesting is that it's blowing out a 5,000 light year long relativistic blowtorch off the top of that. So high energy particles streaming out of this thing, extending for at least 5,000 light years away from it and slowly precessing. So it's spraying the inside of its galaxy there with this high energy stuff. Can't be good for any genetics there, so it's nice to see it from our point of view, which is about 50 million light years away. So the Hubble managed to take a really good shot of this a few years back. So you can see at the core region there, the very nucleus of the galaxy where the source is there, and you can see this thing spraying out. As I say, the extent is about 5,000 light years. In your telescope, if you could see this, it's very hard to see this visually. You really got to do it photographically. Some amateurs have reported seeing this thing through larger telescopes, but it's only about 20 arc seconds long. So it's about the same diameter, maybe a little bit bigger than the ball of Saturn seen through a telescope. But it's also buried in that mass of the galaxy. But with digital cameras, we can stretch the data, and so we can play as I showed you. So that's the Hubble image, and my humble attempt is there. Wow. So yeah, that's diving right into the core of the galaxy, and you can still see the jet blasting out. Thank you. Thank you. Fascinating object. All right, last one I have for you here. This is a time lapse I shot about a week and a half ago. Milky Way, this is 3 hours, shortest night of the year, no moon up there. Just a time lapse I shot with the Canon 60DA and 8mm wide-angle fisheye lens on a star tracker as well, set to half the tracking rate. So what you'll notice is that the foreground is actually slowly panning as well as the galaxy is moving. But this is sped up about 800 times, so you've got 3 hours here of night in about 14 seconds. And if you can run that, Chris, there. You can see some interesting clouds moving through there. There's one meteor that was visible early in the sequence there. The flashes that you see are just periodically turning on lights and things like that when we were imaging there. So yeah, so there you can see that's right in basically my backyard there, and you have a nice definition of the Milky Way all the way down to the tree line there. That's what I've got for you. Have a great weekend.
Rajesh.
Good evening, everyone. So I was actually there on that same night. I was taking Paul's astrophotography class during the spring, and during this night, he invited me over to take some astrophotography at his place. So I just borrowed this image from Paul, and during this night, I shot M13 and M27. So M13 is right over there, and this is my attempt at it. So this is my first time trying something like this with attaching my camera to a telescope. So I was actually glad I got this image. It's a series of 5-minute exposures. I had 6 images in total, which I stacked together to get this image. And my next one was M27. So and this is my attempt at it. So thank you very much.
For first-time astrophotography, that's pretty impressive. Okay, tonight's meeting, typically our meetings are streamed live over the intranet, and you can watch them later on Ustream. That's not happening tonight, as I mentioned in an email to RASC members. This meeting has been recorded or is being recorded, and it'll be posted on YouTube. So I'll send out an email to all RASC members, and we'll also post a link on our webpage. Next slide. A couple of announcements before we close. Who sent it to me? Dave Chisholm sent me a note reminding me that there is a star party tomorrow, I believe, at North Frontenac Dark Sky Preserve. This is the one that's been getting a lot of attention lately. I'm told it's very close to Nirvana in terms of its the dark sky, and it's accessible. It's powered. There's facilities there. Actually even washrooms and power and a cement pad that we can set up and so forth. It seems hearing good things about that. So it's tomorrow. I wanted to mention one thing before I forget. Doug George also reminded me that Starfest is coming up August 21st to the 24th. There's a lot of pamphlets up front. If you're interested in this Canada's premier star exhibition, astronomy show exhibition. What's the word? Cooperative. There you go. It's really something to see. So thanks. All right, Estelle's pick of the month is here. Once again, the library is just right around the corner. Next slide. And this is it. After the meeting, we meet at Kelsey's, just up the road. I want to thank everyone. I know it was a jam-packed night. This evening was a number of things came together, and we tried to move things, but it turned out that there was a lot more in this meeting. So I apologize for the rush. Outstanding job, Glenn, Richard, Frank, and all of our other regular presenters and observers. It's really well done. We have we're fortunate to have a strong center. 105 this. Next meeting is in August. It's the second Friday of the month. And Peter Heyman, who I didn't see here tonight. Peter is going to McMaster. He's going to be talking about black holes and their Earth analogs. Okay, I've seen his work, and I've seen what he's planning to talk about. It'll be pretty impressive. So I have a lot of respect for Peter. He's been very much an active person in our club, and hopefully you can hope you can make it. And also another person, Bianca Deuce, is going to be talking about crater morphology. Okay, so I think that's it. Well, that closes the meeting here. April, can you help me with the door prizes here? And thank you, everyone. And